Hello all, welcome back to digital image processing video session. Today is the sixth session. In the previous session, we have covered complex numbers, Fourier series, impulse and their shifting properties, convolution, Fourier transform of one continuous variable. Today we are going to discuss discrete Fourier transform of two variables. Today we are going to discuss discrete Fourier transform of two variables, the 2D impulse and its shifting property, the 2D continuous Fourier transform pair, two-dimensional sampling and 2D sampling theorem, aliasing in images, the 2D discrete Fourier transform and its inverse. Then we will go for multiple choice question. The discrete Fourier transform of two variables, the 2D impulse and its shifting property. Impulse of two continuous variables t and z is given by the expression delta of t comma z is equal to infinity if t is equal to z is equal to 0, otherwise 0. That means the variables t and z are 0, then delta of t comma z is infinity. In all other values it is 0. Means it's everywhere it is 0 except at the origin. Impulse of two continuous variables t and z is given by the integral equation, that is integral of minus infinity to plus infinity, again integral of minus infinity to plus infinity, delta of t comma z into dt into z dz is equal to 1. That is integral of minus infinity to plus infinity, integral of minus infinity to plus infinity, f of t comma z to delta of t comma z into dt into dz is equal to f of 0 comma 0. Okay, where t and z are variables. The 1D impulse and its shifting property, 1D discrete impulse is given like this, that is f of t comma z, that is double integral of f of t comma z into delta of t comma z into dt into dz is equal to f of 0 comma 0, double integral of f of t comma z delta of t minus t naught comma z minus z naught into dt into dz is equal to f of t naught comma z naught. That is when shifted to t minus t naught, shifting from t to position t to t minus t naught, z to z minus z naught, we are getting f of t naught comma z naught. The 2D impulse and its shifting property, 2D discrete impulse is given by the equation delta of x comma y is equal to 1 if x is equal to y is equal to 0, otherwise 0. That is everywhere the impulse function value is 0 except at origin, that is except at x is equal to 0, y is equal to 0. When x is equal to 0, variables x is equal to 0, y is equal to 0, its value become, impulse value become 1. In otherwise it becomes 0. For all other values of x and y, impulse delta of x comma y is equal to 0. Shifting property again given by summation expression, that is summation of x is equal to summation of f of x comma y into delta of x comma y, that is double summation where x varies from minus infinity to plus infinity, y also varies from minus infinity to plus infinity, is equal to f of 0 comma 0. That is f of x comma y delta of x minus x naught y minus y naught, it is summation of double summation of x is equal to minus infinity to plus infinity, y is equal to minus infinity to plus infinity, f of x comma y into delta of x minus x naught y minus y naught is equal to f of x naught comma y naught. From the figure you can see two-dimensional unit discrete impulse variables x and y are discrete. The 2D continuous Fourier transform pair, the function f of t comma z, continuous function of two continuous variables t and z. The 2D continuous Fourier transform pair is given by f of mu comma v is equal to double integral of f of t comma z into e to the power of minus j2 pi into mu t plus vz into dt into dz. The integral varies from minus infinity to plus infinity, where mu and v are frequency variables, t and z are spatial variables, and f of t comma z is equal to double integral of f of mu comma v into e to the power of j2 pi into mu t plus vz into du into d mu into dv, and integration varies from minus infinity to plus infinity, both the integrals. Example, obtaining the 2D Fourier transform of a simple function is given by the expression f of mu comma v is equal to double integral of f of t comma z into e to the power of minus j2 pi into mu t plus vz into dt into dz, that is equal to integral of minus t by 2 to plus t by 2 into integral of minus z by 2 to plus z by 2 a into e to the power of minus j2 pi into mu t plus vz into dt into dz, that is equal to at into z of sin pi mu t by pi mu t into sin of pi vz by pi vz. The magnitude spectrum is given by the expression magnitude of f of mu comma v is equal to atz into magnitude of sin pi mu tau by pi mu t into sin of pi vz by pi vz. That is the magnitude spectrum expression. So you can see here from the diagram 2D function and the spectrum of that function. So here at the t axis the block is longer, and at mu axis the spectrum is more contracted. So larger the values of t comma z, more contraction of the spectrum, lesser the values of t and z, less contraction of the spectrum. Two-dimensional sampling and 2D sampling theorem. Sampling in Two-dimensional can be modeled using the sampling function, that is using 2D impulse train. Delta of delta t into delta z of t comma z is equal to double summation, that is m limits from minus infinity to plus infinity, n limits from minus infinity to plus infinity, delta of t minus m into delta t comma z minus n into delta z, where delta t and delta z are the separations between samples along the t and z axis of the continuous function. Multiplying f of t comma z by delta of delta t into delta z of t comma z yields the sampled function. From the figure, you can see the two-dimensional impulse train. The function f of t comma z is said to be band limited if its Fourier transform is 0 outside of a rectangle minus mu max comma plus mu max and minus v max comma plus v max. 2D sampling theorem. A continuous band limited function f of t comma z can be recovered with no error from set of its sample if the sample intervals are delta t is less than 1 by 2 mu max and delta z is less than 1 by 2 v max. Okay, that means the sampling rate should be twice the maximum frequency content. Highest frequency content, it is twice the maximum highest frequency content. Then we can recover the signal without any error, without any loss. That is the statement of sampling theorem. Here in the diagram, you can see the oversampled and undersampled band limited functions. This is oversampled, this is undersampled. In the oversampled, the dash indicates the footprint of ideal low pass filter. The dash indicates the footprint of an ideal low pass filter to reduce the error. Aliasing in images. Aliasing is a phenomenon of higher frequency components to overcome the identity of low frequency components. To avoid aliasing, defocusing the scene which is to be digitized, that is attenuation of high frequencies before the image is sampled. That is what anti-aliasing technique we have to use to minimize the aliasing effects. Example, here you can see sampling checkboards whose squares are of size 16 cross 6 pixels. In the figure, A and B length of the sides of the square are 16 and 6 pixels respectively, and aliasing is visually negligible. In C and D, sides of the squares are 0.9174 and 0.4789 pixels respectively, and the results show significant aliasing. The figure D is normal image. So effects of aliasing can be reduced by slightly defocusing the seed to be digitized, that is attenuation of high frequencies before the image is sampled. That is anti-aliasing. Effects of aliasing generally are worsened when the size of a digital image is reduced. You can see here the aliasing effect from this diagram, from this image. That is illustration of aliasing on resampled images. The same image having the aliasing effect. The A is in the figure, the image A, digital image with negligible visual aliasing. B is result of resizing the image to 50% of its original size by pixel deletion. Aliasing is clearly visible. C is resulting of blurring image in A with 3x3 averaging filter prior to resizing. The image is slightly more blurred than B, but aliasing is not longer objectionable. That is blurring prior to scaling. Moire patterns. So in optics, beat patterns produced between two gratings of approximately equal spacing. Example here from the figure, these are ink drying, not digitized patterns. Superimposing one pattern on the other is equivalent mathematically to multiplying the patterns. Here a newspaper image and an enlargement of showing how off-tone dots are arranged to render shades of gray. The 2D discrete Fourier transform and its inverse. The 2D discrete Fourier transform of a digital image f of xy of size m cross n is given by the expression f of mu comma v is equal to double summation of x is equal to 0 to m minus 1 and y is equal to 0 to n minus 1 f of x comma y into e to the power of minus j 2 pi mu x by m plus vy by n, where f of xy is a digital image of size m cross n. Inverse discrete Fourier transform is obtained by this expression f of x comma y is equal to 1 by mn into summation mu is equal to 0 to m minus 1 into summation v is equal to 0 to n minus 1 f of mu comma v into e to the power of j 2 pi of mu x by m plus vy by n. So then we will go for multiple choice questions. 2D Fourier transform and its inverse are infinitely aperiodic, periodic, linear, non-linear. The answer is periodic. The band limited function can be recovered from its samples if the acquired samples are at rate twice the highest frequency. This theorem is called sampling theorem, convolution theorem, initial value theorem, final value theorem. The answer is sampling theorem. Fourier transform domain is frequency domain, spatial domain, Fourier domain, time domain. The answer is frequency domain. Fourier transform of two continuous functions that are inverse of each other is called Fourier series pair, Fourier transform pair, Fourier series, Fourier transform. Answer is Fourier transform pair. Impulse has the property called rotating property, shifting property, additive property, additive inverse. The answer is shifting property. Thinking of image is viewed as undersampling, oversampling, critical sampling, Nyquist sampling. The answer is undersampling. Continuous band limited function can be recovered with no error if sampled intervals are less than 1 by 2 mu max is the statement of 2D sampling series, 3D sampling theorem, 1D sampling theorem, 2D sampling theorem. The answer is 2D sampling theorem. Forward and inverse Fourier transforms exist for the samples having values integers, infinite, finite, discrete. Answer is finite. The common example of 2D interpolation is image, enhancement, sharpening, blurring, resizing. The answer is image resizing. The impulse S of t comma v is function having one variable, two variables, three variables, four variables. The answer is two variables. So t and v have two variables. Okay, today we will end the session here. Thank you all. Thank you.